So once again, we want to cover some broad concepts that relate to scientific computing applications, and there's some background in computer science that is helpful. So we'll have a brief overview of computer architecture, the two types of digital information. We'll get into base 2 and binary values. It has to do with the Boolean concept of true and false. We'll talk about what is considered to be like the holy trinity or hat trick of programming and scientific applications, the origins of procedural programming and the new and improved methods, and what we would call the secret sauce of coding made easy. So once again, we are going to be introducing some light programming in the course where you create your own scientific computing applications, but we'll also use a lot of prepackaged applications for scientific qualitative and quantitative analysis. Pseudocode as a foundation for prototypes and production coding. So if you'll excuse me, I have to just allow somebody into the class. So whenever somebody drops, basically what we're going to do is pause for a second and let them back in. And that's just a necessary evil given where we are. So this is the basic computer architecture as devised by John von Neumann, a pioneer in the computing engineering discipline. And he basically devised the same design that's used today. So we have a CPU or central processing unit, which has the arithmetic logic unit. That's the one that actually crunches, performs the instructions and the calculations. There are memory registers that are super fast memory that are kind of like the memory over here. There's a controller. You have input and output. Like
Dr. Kensop,
yes.
Should we be seeing your screen?
Oh, you don't see the screen?
No, we don't.
Oh, well, I'm very glad you said something. Thank you so much. And that's Raquel.
Yes.
Okay. Thank you, Raquel. I'll put an extra bonus in your Christmas envelope this year for calling that out to me, because I would not like to do all of this for a recording only to find out that nobody saw the stuff. So, all right, so here we have the basic architecture. And the two types of digital information are data and instructions. So you have digital information, generic digital information, we would call data, right? And then there are programming instructions that are also, it's also a form of digital information, but more importantly, these are instructions that are designed to operate on that data. And this is the thing that made scientific computing possible, is that you could have data from a laboratory experiment, all the outcomes and results, and then you could use the instructions to automate the processing of that data. I know I'm speaking pretty plain stuff at this point. Computers can only handle, this is where it gets interesting, computers can only handle two values, on, off, or open and closed, or true and false, yes or no. So for those of you who are computer science students, you're rolling your eyes now because you've already heard this. We've already been through this. But for those of you who are outside the discipline, who are joining us from other STEM majors, just hang on a second. So I want to explain that. So what? So you have two different values. It's the two conditions, true and false, that form the basis for logical conditions and decisions that follow. So you can say, if the value of this experimental output exceeds 10 kilograms, then there's a decision that follows. Scientific computing applications can automate your experimental process, which is really good. We also said that data management decisions have to be embedded into your process in order for data analysis to occur. So there's a connection between data management and data analysis, and data management has to do with these logical conditions. So you're only going to collect certain kinds of data types. Now that you have the precursors, you can work in any programming language. right? So if you can't find a scientific computing application that has the features and functionality that you want, you can create one. And we're going to do that in this class. So when you're developing your coding skills, I would suggest a language-centered approach. I'm interested in doing some advanced studies in this area, and I think it may be the basis of a PhD thesis for me, because I think that there's been a lot of lost time in the computer sciences trying to get people to fall in love with coding, and we've been using a math-centered approach. No offense to any of you who are applied math majors. A lot of math folks get it, but in some cases, your predisposition to mathematics can be a handicap, and we'll give you an example of that in just a minute. There are special practices. You need to know that you want to create intentional statements and review them from the right to the left. This is counterintuitive. So let's say that again. When you're coding and you're writing a programming statement of instruction for the computer to execute, it reads from the right to the left, not like you do. This is really important to understand later on in our course when we devise some very simple programs. The number of leading spaces is important. If you're going to indent with 4 spaces, make sure you indent all the time. So a lot of coding development platforms are very kind of picky, and that can create a sour taste in the mouths of a lot of people who try coding for the first time. It's the logical case that's often neglected the most. You want to frame whatever it is you want to accomplish with your software in a logical condition, a true or false, a case that's presented by values that become the basis for decisions that trigger other coding statements. This logic, this basic core logic that I've just described, is really where good programmers earn most of their money. They're capable of saying, okay, what is it we want to do? What's the logical condition? What are the values that are required to evaluate the condition? Once that condition is tested for a decision, what comes next with other coding statements? Seems pretty simple, and it's best to work simple terms when you first start with this. Okay, indispensable components: inputs, process, and outputs. There are keywords, there are operators, and there's syntax, or the rules for how to order these, right? So a lot of times when people have really poor experiences in their first exposure to scientific computing applications and a little bit of coding, they run screaming from the room because nobody took the time to explain. Okay, you have to think in terms of the inputs for the software, the process that is the operations on those inputs, the outputs that you want to expect as a result of the calculations or instructions, and then the keywords and operators and syntax for whatever programming language you're going to use. Any questions at this point? All right. If I don't hear somebody say no, I'm going to ask again.
No.
Are we good? Okay. Thank you. All right. So the dynamic duo, right? So adding Boolean logic is like adding concrete and water to sand. You take the condition you can test, where the outcome is true or false, inputs for decisions, you branch or jump to a different procedure or a different instruction, right? Oops. So when we talk about the dynamic duo, it's a condition you can test, right, with the inputs, and that's it's those two things, all right? It's a condition that you can test. If you have a condition you can't test, you're kind of dead in the water. So whenever you're thinking about a scientific computing application to automate your experiment or to manage your data or to analyze your data, you want to think in terms of a condition that you can test. It's like a 1-2 punch, right? When we say test, we're saying the outcome is true or false. And then, of course, that becomes the basis for following decisions. It's the condition you can test. All right, 3 Musketeers of coding statements. So if you look at 3 coding statements that perform the real work of any method, module, or function in all of scientific computing, even at the national laboratories, Lawrence Livermore in Silicon Valley, where they're building a new version of the sun so that a single barrel of seawater can power a city of 50,000 folks for a year. That's what they're doing right now. It's called, what is it called? It is an ignition platform. They're creating the conditions for fusion inside. They want to create a better version of fusion. That's what they're working on in Lawrence Livermore in Silicon Valley right now. They use these same 3 main components. I call them the 3 Musketeers, right? So there's a sequence of statements that provide the flow and order, or the process, right? What is it what do you need to process in terms of the data? And it helps to just draw that out on a whiteboard. Just take any sheet of paper or a whiteboard and start drawing the flow and order, the process. There are decision statements that apply to that process, right? The criteria. What are the criteria for decision points? The forks or breakpoints. If this is true, go here. If that's false, go there. So those are the criteria. And the last one, the repetition statements. So in every programming development platform or language or integrated development environment, they call that an IDE, Visual Studio, JetBrains for Java, right? There are sequence statements, there are decision statements, and repetition statements. There's an order of steps, that's sequence. There are decision statements that involve the logic. If so, then true, yes. If not, then do else, right? Decision statements. And then there are repetition statements. Oh, do this, do this, do this, do this, until this is no longer false. That's it, in a nutshell. If you wanted to know the core of computer science as a discipline, it's creating algorithms that have to do with step-by-step instructions, decision statements, and repetition. That's it. And that's it in a nutshell. And we're gonna provide the baby steps for that so that you can do some of that, create your own custom application in our course. So, sensible process to develop coding skills, believe it or not, is to spend a little more time in preparation up front. You see a lot of people that want to do something for a science experiment and they dive right in and they start writing code. It's not the way to do it. You want to look at some things up front, and you want to take a little time to determine mostly the outputs. So an IPO table, and this is a tool that you can use. IPO stands for input, process, and output. It's a simple table, 3-column table. You'll see an example in just a second. A flow chart. So what are the step-by-steps and the decision points? That's optional, but it's good to have because then you can kind of keep that in front of you as you're writing. And then the pseudocode. You don't want to write in the code. There are a lot of folks that pride themselves on their mathematical prowess, and they say, well, you know what, programming language, it's basically just another kind of math, and I'm good at that, so I'm going to grind it out, and I'm going to write these. I've had a basic Java course, I had a basic Python course in high school. I'm going to do this. Don't. I'm saying if you want to get good at this, write in plain English. The logical process. Do that first. Take the time. Later on, when we're doing our solutions, when you call me or you text me or you email me to say you want a walkthrough, the first thing I'm going to do is say, show me your IPO table. What are the outputs? What are the inputs? What's the process? Show me your pseudocode. What are the logical steps in the order in plain English? you're using the language side of your brain. That's important here because that's where the logic sits in a language context that allows you to translate to programming statements. I know it doesn't make sense and it may be counterintuitive, but that's the reality. Okay, so variable names. Here's another thing that you want to do. When you talk about a language context, this last item here, the pseudocode, you want to use variable names. So variable names, what's a variable? A variable is an abstract construct. It's a make-believe object. It's an object. It's a container. It's a container object. A variable is a container object that allows you to store data. And you should name it with something other than a single letter. Now, I know that single letter variable names are the pride and joy of every mathematics guru, right? So if you're really good with math, this is your bread and butter. You have all these variable names that use single letters. You have to break that habit. You have to force that change. You want to use a variable name that's a lot more intuitive so that the language side of your brain can be engaged as you're writing the programming statements. You want to use something called camel case with a brief purpose. So you want to have a leading hint about the data type. So a data type, what do we mean by data type in this first bullet point? What can you store in variable? You can store whole numbers. So the data type would be integers. You can store a number with a decimal point. That would be the real data type, or floating point data type. You can store a string of characters, letters, words. That would be string data type, right? So you might include a variable name that has the lowercase letter I for integer, R for real, or S for string, so that when you look at the variable name, you know, oh, there's supposed to be words in here. The reason you do that is because if you get an error when you try to compile your code, it may say something like, this is the wrong data type. And you look and you're like, oh, I have letters where they're supposed to be whole numbers. Problems fix themselves. If you don't do that and you use single variable letters, if you use single letter names for your variables, you'll never pick up on that. And then you'll be banging your head on the wall. And the first couple of how-tos will go great, but then the rest of your programming experience will be terrible. And I don't want to be the professor for those of you that are in the STEM disciplines outside of computer science who run screaming from the room and go, well, that was kind of a nice course, and I learned how to do some interesting things with Excel spreadsheets, but past that, it was all a blur, and I don't ever want to be a programmer, right? I want you to see and appreciate the finer points of how to do this right, so that, and then when some computer science graduate approaches you with a scientific computing application that's written with all single letter variables, you can wag your finger at them and go, no, 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 no. No, no. See, I had a course in how to do this right from a guy who was a systems engineer that worked 20 years in a software engineering context, developing integrated solutions for an entire enterprise on 3 continents and 16 countries. Yeah. And he's saying, that's what you do when you're in kindergarten as a programmer. So for those of you who are computer science students, don't you dare, I'm just saying, getting a little animated here to mix it up so that people don't go to sleep. If you're a computer science student and you know who I am already, when we do our solutions later in this course, don't you dare use a single letter variable with me, okay? Because I'm going to do more than wag my finger at you, okay? And now I've let out a dirty, nasty secret about computer science folk. A bad example, I. A good example, integer current temperature. So let's see how this works. Without these helps, here's an example of code that was written with a single letter variable. Oh, you have some functional statements there, but right there you can see that there's some, oh my gosh, I mean, it's not really clear what's going on there. Here's what happens. Let's take a simple example of a scientific computing application that helps you control the temperature, the ambient temperature in the environment where you're mixing chemicals. Is everybody with me? I have an air conditioner. Is everybody with me? Can somebody cue up their mic and say, yeah, we're still with you?
I'm here.
Yeah.
Okay, good. So let's say we have a simple scientific computing application that helps to automate your experimental method. And one of the things you have to do is control the ambient temperature in the environment where you're mixing chemicals. Given an air conditioner, an AC, if the, and that's this whole number temperature, right? If the whole number current temperature is less than or equal to 76, then the Boolean air conditioner state is equal to off, on or off, true or false, right? The Boolean, I say boo because I want to indicate the kind of data type. Boolean is a data type, true or false, on or off. I have a Boolean data type. I want to store on or off, 1 or 0, true or false in that variable. And the AC state is equal to off. Else, the Boolean AC state is equal to on. I guess what I'm saying is that this is understandable code. I know what it's doing. I know what the conditions are. I know where the triggers are. It's not hard to write. It's not hard to understand. It does the job. If you go I equals I plus 1, something or other, debug is a much plainer process. So a lot of times you get inputs. If you have an input where there's a sensor and the input is providing decimal numbers for the input and supposed to provide whole numbers, you might get an error in your when you try to run the code, right? All right, so let me prove to you just how deadly single letter variables can be in the programming context. We're going to take a slight break here. I want everybody to just pause for a moment, stand up and stretch, you know. I'm going to grab a drink of water here real quick, okay? And I want you to do the same. And then we're gonna take a quick side trip to show you just how bad and nasty single letter variables can cause a problem if you're trying to work with scientific computing applications. Okay. All right. So you were taught in algebra that as long as you do the same on both sides of the equal sign for an equation, we're going to use the example for what happens when you use single letter variables in the context of simple algebra. And when you were being taught algebra for the first time, true or false, as long as you do like divide by 2 on the left side of the equal sign and divide by 2 on the right side of the equal sign, nothing's changed. Does everybody understand what I'm talking about? Yes, no, maybe? Okay, well, let's just keep going with the example. Let's say we have an equation that says A equals, has anyone seen this before? Has anyone seen me demonstrate this or show this before?
No.
I have not.
Okay, so let's say we have a simple algebra equation and we're using a single letter variable. Because we're used to doing algebra that way, right? I mean, how many years did we do algebra? Years, right? It's kind of a reflex, isn't it? I'm saying break the reflex, right? Let's take this simple equation, A equals B. If I do both, if I multiply both sides by A, I haven't changed anything. So if I multiply the A by A, I have A squared. And then what do I have on the right side? Anyone?
A times B.
A times B, that's correct. AB. Everybody with me?
Yes.
Okay. Too easy to get lost in the process when you're doing a scientific computing application with programming statements, much more so than algebra. But let's just show you how bad it gets even in algebra if all you're using is single letter variables. I'm going to subtract B squared from both sides. Now, what was my previous statement? A squared equals AB, right? So I'm going to subtract B squared from both sides. Have I changed anything? Put another way, does A still equal B?
No.
It does.
Oh.
It does.
It does. Yeah, I threw the bait out. I'm glad you took it. You know that something's going to blow up, obviously, right? I mean, that's the whole premise of this demonstration. But we started with A equals B, and as long as I do the same thing on both sides, I shouldn't have a problem, right? So if we solve back down, if we reverse the process, we'll end up with A equals B. We'll still end up with A equals B. We can just reverse it. Instead of subtracting, we can add b squared, and the b squareds cancel out, right? Let's continue though. Then let's factor both of these terms. Everybody remembers factoring, right? Ooh, factoring. A squared minus b squared can be factored into a plus b times a minus b, and on the right side we have b times, in parentheses, a minus b. Everybody with me? Does a still equal b? Yes, a still equals b. I'm going to do the same thing on both sides now. I'm going to divide both sides by a minus b. This is what I'm going to do. Does everybody see what I'm doing?
Yes.
Yep.
Okay. Now, I'm going to substitute b for a, because in the beginning we said a equals b. Isn't that correct? If a equals b and we haven't changed anything, if a still equals b, I can substitute b for a. So we started with a equals b. So now I have on the left b. I've substituted the a here with a b. B plus b equals b. Well, wait a minute now. B plus b equals b. That's the same as 2b is equal to 1b. And if I divide both sides by b, I've just proven that 2 equals 1. Holy buckets. What's going on here? What happened? What happened? How is it that 2 equals 1? If a equals b, and I did what I was supposed to do on both sides of the equal sign, according to algebra, I should not be in a place where I've just proven that 2 equals 1. So this is a classic example of what we would call a logic error. If we took the steps of instructions in a programming application and we followed this algebra process, we would end up with an error, and there would be a logic error, and it would go boom. It might even crash the system. Hackers love this kind of stuff. They love tangling a computer around its head to watch it go boom. What we have here is a case. Does anybody know what happened? Do we have any algebra? Does anyone want to take a guess at what went wrong here?
Maybe if you could go back a slide.
I'll give you a hint. Look at this statement. We started with A equals B. So what does A minus B equal if A equals B?
Oh, yeah, we divided
0.
by 0.
It's 0. Yeah. And a young lady, I heard her voice. Say it again, please.
Oh, we divided by 0.
Exactly. If A equals B, then A minus B is 0. We've divided by by 0. A minus B is 0. So you evaluate this expression to be 0. Can you divide by 0?
Yeah.
No. Actually, you can. We just did. It's disastrous. See, for years you've been saying division by 0 is impossible. That's not accurate. It is not an accurate statement to say that division by 0 is impossible. It is possible. It's just disastrous because then 2 equals 1, right? Things get flipped inside out. And then your scientific computing application produces data results that everybody laughs at. We want to be able to understand simple mistakes, and that's why we're going to insist on some things during this course. One is, I need everyone to use descriptive variable names. When we have application objects, data tables, data queries, database forms, if we have variables in our program that we've created in a custom context, we've created our own custom application, I'm going to insist on using descriptive variable names. Because when we get a debug error, when we try to run it and we get an error, I don't want you calling me at 11 o'clock at night saying, I know this is worth 10 points on my final average, but I still don't get it, and I need your help. I mean, I'll be there for you, and I'll answer the call at 11 o'clock, but I'd much rather have a scenario where you look at what's on the screen, and because you used something other than a single letter variable or a name, right, for that object, that we've got more to go with. We've got more definition in the scenario, and we can pin the tail on the donkey a lot faster. Right here, this is a trick, and it was actually carried, it was part of a Mensa exam. For those of you that are interested in becoming part of the elite group of the world's smartest people, there's an organization called Mensa. If you have an IQ that's north of like 170 or 180, you can join Mensa. And this is one of the problems that they give you. Okay, tell me what's wrong on this. And a lot of people can't pick it out very fast because this is embedded inside. The point is that it's harder to see that you're dividing by 0 because you're using a single letter variable. It's easy to get lost in the weeds. Any questions? Okay, so when we combine B plus B, all right, you've seen this. Coding in a specific language flows directly from the pseudocode. The other reason that you want to use plain English in your pseudocode, and you want to state the logic plainly in your logical programming statements, and you want to use plain English, is because Python uses plain English for its coding terms. Its functions are plain English. When you use Java or you use C++ or you use some of those other funky languages, it's not so easy, but we're going to be using Python a lot. We're going to be using R, which is used for Ruby, which is used for cloud applications. Very cool language, very good at statistical analysis. R is a plain English coding language like Python. If you have it in pseudocode to begin with, you can simply write out the Python from the pseudocode. It's a thing of beauty. We've even had some people change their majors from where they are to become the best computer science graduates I've ever seen. That happened in the campus I was at before I came here, and I've seen it since I've been here at UVI in the last 4 years. Now, I know many of you are very committed to your discipline, and it's unlikely that you would jump ship and become a computer scientist. But wouldn't it be cool if you're that person in the experiment for that summer research that actually knew how to generate the data that you needed for your poster presentation so you can get on the plane and fly to DC and show and tell to the world so somebody pays for your graduate program? Hell yeah, that would be cool.
Sounds pretty cool.
Yeah, that's what I'm offering here. That's what I want you to get jazzed about. It's easier to do something when you're excited. Python is an interpreted language that uses English along with R. Now, once you have the software working, it's easy to pivot from the pseudocode into Java, into C++, and then compile a formal application that's performance tuned for fast performance. So a compiled language is written from the pseudocode, okay? Python is ideal for the prototypes, and the compiled languages are ideal for production use. And before somebody beats me up and says, Java is an interpreted language, well, yeah, kind of, sort of. It's kind of a hybrid, like C#. And yeah, that's a finer point. But I'm trying to make a statement here that programming languages like R and Python and BASIC are more English-like, and that's where we want to start. We don't want to start with the really funky ones like Java and C++. Not right away. Any questions?
No, sir, not at the moment.
Okay. So Excel is an excellent primer on how to learn the programming process, the scientific computing application process. That's because in the coding process, you're dealing with inputs. We would call that data collection. We would be dealing with processing. That would be called analysis. And then the outputs would be a pretty graph or a chart or a whisker plot or a linear regression. Those are pattern recognition tasks. We're recognizing a pattern. We're generating a graphical output. Excel does all three of these, including automation. You can turn on a switch in Excel, perform a set of builds, and then hit the replay button, and it'll do it over and over and over again. I've seen this with 1,000 cells. I've seen a build for 1,000 cells with formulas performed in a 90-minute span while the recording was going. And then when they do it again, they put in a different value, hit the replay, and 90 minutes worth of stuff happens in 90 milliseconds. Ooh, that's just sexy. I don't know how else to describe it, but you're gonna see that later in the season. You're gonna see this on the screen. You're gonna click a button, and 90 minutes worth of work is gonna happen in less than a blink of an eye, and it's gonna feel so good. Because you're going to have a life at that point. You won't have to spend the weekend grinding data manually. You're going to be using scientific computing applications, so you have time, you know, for a date. Anyway, Excel, you notice I misspelled it. The variables that make up the Excel spreadsheet are actually called cells. It's a box, it's a container, it stores data, it stores instructions, it is a variable. And it's a nice way of framing your introduction to scientific computing applications. Okay, so I'm going to stop sharing the screen for just a second here. I'd like to see how we're doing on time. On Thursday, I'm going to take this to the next level. I know that you may have other classes that start at 1 p.m. Does anyone have any questions about input, process, outputs, logical conditions, testing for conditions, decisions based on conditions, any of that?
Not really. It's pretty much a review of computer architecture for me.
Isn't it? Yeah, there's some of that built in there. Yeah, yeah. Oh, I'm glad you recognize some of those things. Yep.
Yeah.
Anyone else? Any other questions? Okay, I'm going to stop recording.